All right, we're going to finish off gas laws here with section 5. We get to our final gas law, which is called Dalton's Law of Partial Pressures. So before we get into it, I just want to recap the gas laws we've talked about. We first talked about the ideal gas law, which was PV equals nRT. This was our very first gas law that gave us a chance to look at how all four variables, pressure, volume, moles, and temperature, were all related to each other. We then took that ideal gas law and we applied it to what we called the change gas laws. And there was a collection of gas laws that basically all came from the same gas law, the combined gas law, which really was just a derivative of this. And in the change gas laws, we looked at what happens when we change a condition about a gas. We change its volume, its pressure. We want to see how it affects the final condition. In this final section with Dalton's Law, we are now looking at when gases mix together. So in a mixture of gases, Dalton's Law states that each gas is going to exert a pressure as though it were by itself. This is known as a partial pressure. So real simply, let's take a look at, let's say this was gas 1, this was gas 2. Actually, I shouldn't say 1 and 2. Let's say A and B, since that's what we got in the equation. So this was gas A, this was gas B, this is gas C. What Dalton's Law states is that these gases, when they're separated, have a certain pressure. These are known as their partial pressures. If you were to take these three gases and mix them together into one container, how would you know what the final pressure is? Very simply, you take their pressures and you add them up to get the total. So 300 plus 600 plus 450 would give you a total pressure of 1350 kilopascals. And that's it. That's Dalton's Law. Really basic as far as this application of it. While I have this on the screen, I want to point out that, okay, you have three gases in here now. You have gas A, B, and C. What's the pressure of gas A now that it's mixed in here? It is still 300 kilopascals. The pressure of gas A doesn't change. Even though it's been mixed now, it's still going to be the same. That's what that means up here. Each gas exerts a pressure as though it were by itself. So gas A doesn't matter, or doesn't care that it's now mixed with gas B and gas C. It still exerts its same pressure. It just happens to be now in one container. So you can find the total pressure by just adding up the partial pressures of each individual gas. Now, there's going to be different applications of Dalton's Law, and so now let's take a look at what those applications are. So you're mixing things, right? And anytime you have a mixture, you always have fractions. So for example, okay, let's say we were looking at a room that had, 4 boys and 6 girls, right? There's a mixture of people. So you have fractions. You would say, okay, well, the fraction of boys is 4 out of 10, and the fraction of girls is 6 out of 10, right? That's intuitive. That's just basic math. In the same way, when you're mixing different gases together, each gas has its own fraction. We call that a mole fraction. This is just another way of us showing the quantity of a gas in a mixture of gases. So first of all, the mole fraction, I want you to notice what the symbology is. It's an italicized X and then sub whatever the gas is. So generically, you would say sub A, but we could have what's the mole fraction of hydrogen gas? What's the mole fraction of nitrogen gas? So on and so forth. But the idea is very simple. If you wanted to know the mole fraction of any gas, just take however many moles of that gas there are and divide it by the total, just like we would if we were doing the boys and the girls fraction. And then what you can do is you can figure out what the partial pressure is for that gas by taking the total pressure and then multiplying it by the mole fraction. This may seem, complicated, but it's actually pretty intuitive. So let's say, for example, you had this container, right? And you had two gases. You had gas A and gas B. And let's say I told you that the total pressure, the total pressure of this entire container with both of these gases, I told you it was 10 atmospheres of pressure, okay? And you were looking at the quantity of gas A and gas B, and I told you that the mole fraction for gas A was 0.7 0.7. And mole fractions are unitless, by the way, because think about it. If you're doing moles divided by moles, the moles cancel out. So it's a unitless number. So the mole fraction for gas A, let's say I'm telling you, it's 0.7. That's the same thing as saying 70% of this mixture is gas A. So to figure out what the partial pressure is for gas A, in other words, what's the pressure just from gas A, you would say, well, okay, what's the total pressure? Total pressure is 10 atmospheres. And what's 70% of that? What's 70% of 10 atmospheres? So the partial pressure for just gas A would be 7 atmospheres of pressure. That's intuitive, right? That makes basic sense based on math. There's actually very little chemistry going on with Dalton's law. It's really more math. Just a reminder, mole fractions should always be less than 1. So whenever you're finding out a mole fraction, if you get a number that's greater than 1, you did something wrong. Which is understandable because 4/3 of people in the world have problems with fractions. So make sure it's less than 1. Also, when you're figuring out what your mole fractions are, they should all add up to be equal to 1 when you find out what they are. And then, reminder again, mole fractions are unitless. And this one's kind of a weird one because I harp on you so much. Make sure you have units. Make sure you have units. But for mole fractions, there actually aren't any units. So you need to make sure that you are writing them unitless. Last thing that I should mention here, even though it says fractions, really that's kind of a misnomer. When I say mole fractions, really what I want decimals. Because unlike our boy and girl example that we did up here where you're counting, when you're talking about moles is a measured value, not counting. So in other words, it's dictated by significant figures. So you can't do sig figs with a fraction, right? You can only do sig figs with a decimal. So you'll see that when we start doing some examples here. All right. Another way you can do a mole fraction is this. Okay, what if I gave you this scenario? All right, what if I told you, you had this container with 2 gases, gas A and gas B, and I'm going to write my pressure letter there a little bit better. There we go. What if I told you the total pressure was, I'm going to do 10 atmospheres again. Just pick an easy number, okay? And what if I told you the partial pressure for gas A was 2 atmospheres, and the partial pressure for gas B was 8 atmospheres, right? That's why you have a total of 10. And what if I said, okay, I want you to figure out what the mole fraction is for gas A and gas B? You may be like, how can I possibly figure out a mole fraction? I'm not given any moles. I can't figure that out. Well, there's actually a really convenient and useful relationship. Since number of moles and pressure are proportional to each other, as long as the temperature and volume are set, meaning you don't change it, then that means you can actually figure out mole fractions either by taking your part moles divided by total, which is what we did on the previous slide, or you could also figure out mole fraction by taking partial pressure divided by total pressure. And you'll get the same answer. You'll get the same mole fraction. So I could figure out what the mole fraction is for gas A by taking its partial pressure, which is 2 atmospheres, dividing it by my total pressure. And I could end up figuring out that my fraction is 0.2 because the atmospheres are still going to cancel. So remember, mole fractions are always unitless. So you can figure out the mole fraction 2 ways. All right, with all that, that was all Dalton's law. It was just different ways of looking at Dalton's law. Let's look at an example. Let's look at example number 10 together. Let's say 3 gases occupy a steel container. Okay, so I'm going to draw that over the side here. All right, so we have 3 gases in here. We have gas 1, gas 2, and gas 3. All right, and what do we know about them? We know gas 1 has a pressure of 1.30 atm. Gas 2 has a pressure of 3.10 atm. And gas 3 has a pressure of 2.70 atm. 2 questions here. Number 1, what is the total pressure? That one's easy, right? Since we know the individual or partial pressures for those, we can figure out the total by just simply adding those up, right? So we're going to do that. Let's see, 0. We got 1 there, 3, 4, 5, 6, and we carry the 1, 7. So 7.10, okay? I'm adding, so I need to do lowest number of decimal places. All these numbers have 2 decimal places, so my answer should have 2 decimal places. And it's still going to be atmospheres. So my total pressure is 7.10 atmospheres. The second question is asking us, what is the mole fraction for each gas? So like I said before, how are we supposed to figure out mole fraction? We don't have any moles. We don't have moles, but we do have the partial pressure and the total. So we could divide all 3 of these numbers by the total pressure, 7.10 atm. Okay, so I'm going to get it all set up for us here. All right, and we're going to do the math. But before I do the math, I want to point out 2 things. Number 1, the atmospheres are going to cancel out. So our mole fractions will be unitless. Secondly, I want to point out that for sig fig wise, you're taking 3 sig figs divided by 3 sig figs for all 3 of these. So my mole fraction should have 3 sig figs as well. So for the first one, if I do 1.30 divided by 7.10, I end up getting my mole fraction is 0.183 for gas 1. For gas 2, I end up getting my mole fraction is 0.437. And then for the final gas, I end up getting mole fraction of 0.380. And if I add these up, I don't have to, though that's my answers right there. But if I add those up, because I just want to make sure that it equals 1. Remember, all my fractions should equal 1. I get 0.183 plus 0.437 plus 0.38. Perfect. This equals exactly 1. So I know that I did it right. If you add them up and you end up getting like 0.999 or 1.01, that's fine too, because most likely it was just due to sig fig rounding. But if I added them up and got like 0.97, that's a little too off, right? So that, just keep that in mind. So let me erase all of that so that you don't get confused. All right, so what are my answers? Answers for total pressure was 7.10, and my mole fractions are here. This is the same thing as saying 18.3%, 43.7%, and 38.0%. All right, we do have a few more practice problems to do, but we'll do that in the next video.